Welcome today, Prof Desplentere and Ineke Felge for our next lecture. We look forward to a very interesting presentation on advanced rheological characterization for highly sensitive bio-based materials. Before we begin, I would like to briefly introduce Professor Desplentere. He is a PhD in Materials Engineering and is a professor at the Materials Engineering Department of the University Leuven in Belgium, and at the same time head of the Propolis Research Group. Professor Desplentere will jointly give the lecture with Ineke Felge, who has a master in product development as well as a master in polymer processing, and is currently PhD student at the Propolis Research Group. Thank you for being here and taking your time today, and I hand over now to Frederick for the presentation.
Dear all, and today I want to present to you our presentation about advanced rheological characterization for highly sensitive bio-based materials. A small table of context. So first of all, a brief introduction about my research group, Propolis. Then I will recall some working principles for capillary rheometers so that everybody is aware about how they work. Ineke will tell you then about the results for bio-based materials, and then finally I will tell you something more about the upscaling to the real industrial processing for this type of materials. So a small introduction about my research group. We are a research group which is a part of Leuven University, so we are located in Bruges campus, so it's a brand new building and we are there since 3 years now. And currently my group is counting almost 20 persons, so we have a nice mixture of postdoc persons together with 10 PhD researchers. So KU Leuven University, so I will not tell you too much about it, but since 2013 on, KU Leuven have different campuses all over Flanders, so spread within half of Belgium. So, and we are belonging to the Department of Material Science and are belonging to the Faculty of Engineering Technology, which means we are aiming at applied research in collaboration with the industry, also with local industry in our region. In West Flanders province, we have a lot of polymer processing going on. So what about activities within the research group? In fact, we are dealing with the whole range from material characterization to feed information into numerical simulation tools to support the real polymer processing. And then finally, if we have produced parts, we are also aiming to test them. So you know that from numerical simulations you have lots of colors and nice results, but we want also to validate them on real equipment. So we need to have really good material characterization to end up with good numerical simulation results. And that's the whole interplay between those three main activities in the lab. So going from material characterization over numerical simulations towards, let's say, validated polymer processes. Okay, so to come to the topic of today, some brief recap on working principles of capillary rheometers. So maybe most of you know this, but we have some news about this. Let's say a standard capillary rheometer, we have the main aim is to go for a forced transport of material through a narrow capillary. So we always have to deal with, it has to be a small channel and to have high shear rates inside the channel, and we want to have it to have a certain length and to have high enough pressure, but on the other hand it cannot be too long, otherwise we are not sure about which temperature is valid for the material which you are characterizing. So the main aim of today is really having a look what is happening to the test sample which is present within this equipment, and what is especially or what does need special attention if we focus on two highly sensitive bio-based materials. So first of all, we see the test sample over here. we also have the pressure sensor just in front of the capillary. So that's the basic capillary rheometer. So how do you work with this equipment? And typically, the user fills up the whole barrel, so which has typically a diameter, for example, of about 15 millimeters. So this is all cold material which is going in there, and you fill it, almost up to the top. So in that way, you will be able to measure a whole range of shear rates, ranging typically from about 20 reciprocal seconds up to 50,000 reciprocal seconds, depending on the material you want to characterize. In that way, you can measure the pressure as a function of the shear rate which is applied, which is in fact the last step. But before we go to the last step, we have some compaction which is going on, and to be sure that we do not have any air in the material which is loaded into the equipment. So in that way, typically a preheating time is used between 5 and 10 minutes to be sure that the temperature of the sample is as homogeneous as possible. Of course, if we want to heat 50 millimeters of diameter of material, this needs, depending on the thermal conductivity of the material and the specific heat, let's say at least 5 minutes to have it almost the same temperature through the thickness. And this can be calculated using standard formulas from heat transfer, but important to know, you have to wait several minutes before you have an accurate enough temperature, or homogeneous temperature. So once this is completely filled, then you can go for the measuring through the different steps and register the typical pressure profiles as function of time. So measuring times is also maybe taking up to 15 minutes if you for sure encounter also, or if you want to measure lower shear rates. So on the other hand, we in our lab have the let's say a specially designed equipment available, which is kind of variation on the standard capillary rheometer. I call it a shear heated capillary rheometer. Instead of just filling the sample immediately into the measuring room, we put the material below a certain plunger, and as soon as the material is loaded, and we also need to evacuate the air which is possibly entrapped into the material. So a plunger is coming down with a certain speed, and it forces the material which was already there from the previous measurement, it forces it through a gap that also can be controlled. So while this preheating is going on, and this plunger comes down with a controlled speed, and this piston is turning around also with a certain speed. So in that way, we have a kind of shear heating in this region. So a combination of shear heating and conduction. So to heat up the material which is, let's say, in the waiting room, and to come into the kind of measuring chamber. So this allows a much faster homogenization for temperature of this material. So the increase of temperature is much faster. Of course, if it goes really fast, temperature can also be a little bit less homogeneous or less close to the temperature which is asked for at the barrel, but it really increases the heat fast. So we don't have the possibility to have too much degradation. And for sure, and the fact that the temperature in this waiting room is below or it's lower temperature. So in that way, it has lots of advantages on which also Ineke will give you some first results. So and once the material is in this measuring room, of course, measurements can go ahead, which is then indicated in these different steps. So at first, we put the material on top of the previous inserted material. And then once the material is there, this one comes down, and the piston is rotating, and this is done until a certain requested preloading pressure is present. As soon as this pressure is reached, the feeding stops, the rotation stops, and then the standard capillary rheometer measurements starts, and different shear rates are realized, and also pressure is registered. So also the rheological behavior can be measured this way. So before we go to the overview of the obtained results, just a comparison for both of them. So if you have a look to typical measuring times for any kind of materials, so with the, let's say, standard rheological capillary rheometer, you have to take into account a typical measuring time of about 20 minutes, while with this advanced one, you can do it in less than 6 minutes, which is really fast. And okay, you also have to keep in mind that concerning material storage, or let's say history of the material, each time you have to load a new sample in there. So there is no possibility already to prepare your material in a kind of intermediate stage. So in here, okay, you have a kind of pre-treatment already 3 times, so air can evacuate at somewhat lower temperature. So it's a kind of gentle preparation, even in a short time. So, and then, so really focusing on the heating or the thermal loading of the material. In this one, at least 5 to 10 minutes before you have any measuring results. Over here, let's say this preparation phase is only taking 30 seconds. So, and concerning temperatures, so at a typical capillary rheometer, all temperature along the barrel is all the same value, while for the this type of equipment, we keep typically this storage volume at lower temperatures before we go to the measuring room, where temperatures than the one at which we want to perform the shear viscosity measurements. So now I give the floor to one of my PhD students, Ineke Valhe, to show you some first results using this equipment.
Okay, so the next part in this presentation is about rheometry on bio-based polymers. But what are bio-based polymers? Bio-based polymers are plastics or polymers that are fully or partially retrieved from renewable raw materials. These are, for example, corn or sugarcane, starch, and cellulose. And some famous examples of these bio-based polymers are PHA, PLA, PBS, or biopolyethylene or propylene. It's a broad range of materials which are not necessarily also biodegradable, but one that is both bio-based and biodegradable is polylactic acid. And PLA, or polylactic acid, we will use it today as a case study on which we did our experiments. So polylactic acid, or PLA, is a biopolyester, and it typically contains ester bonds, as you can see on the chemical formula on the right. These ester bonds, they tend to degrade when they are exposed to high temperatures. Also moisture or shear stresses can result in degradation of our molecular chains. And there are multiple types of degradation happening at the same time. So we can have thermal degradation, mechanical degradation, oxidative or hydrolysis. All these types result in the same effect, and that is that our molecular weight will decrease, meaning that our long polymer chains, which we want for good mechanical properties, will break down into smaller fragments, and we will see a decrease in our molecular weight. And to show you the importance of degradation during measuring or processing these type of materials, we did some experiments, and we are glad to share our results with you today. So the first one we tested is the influence of the temperature. So what experiment did we do? We took a normal or standard capillary rheometer, and we tested the Ingeo PLA 4043D, which is a typical grade that is used in industry, and we pushed it at a really low shear rate through our capillary, and the shear rate was 100 reciproc seconds, and we made sure also that our moisture level is below the recommended barrier of 250 ppm. So on the right, you can see here our results, and we have our measuring time on the x-axis, which is in seconds, and we have our pressure on the y-axis in megapascal, and we did 3 different temperatures. We used 185, 210, and 230 degrees Celsius, and we pushed it really slowly through the capillary, and we looked at how our pressure is increasing, decreasing, or just evolving over these long measuring times. Because you can see we are here at 2,400 seconds, which is already a long time at a high temperature. So what is clearly on this graph is that at a temperature of 185, we can only see a really small decrease of pressure. But when we go higher in temperature to 210 degrees Celsius, we can see that the drop in pressure is already 11.73%. That's already a lot. But when we increase the temperature even more up to 230 degrees Celsius, we can see a large decrease of 34.37%. And this means that the higher we go in temperature, the more thermal degradation will occur in our material. We did the same experiments with this variant of the capillary rheometer, and we can actually see the same results. So we see the largest decrease in pressure at the highest temperature. And how can we explain this? When we take our start material, it has a certain molecular weight. This represents the length of the chain of our polymer chains, and it is directly linked to our viscosity and our pressure. A low molecular weight will typically have a material with a low viscosity. When we measure or when we process these materials at a high temperature, we expose them to high temperatures, and this means that we will have thermal degradation and chain scission. And chain scission means that our long polymer chains will break down into smaller fragments, leading to a decrease in molecular weight and eventually also a decrease in viscosity and in pressure. And this is the thing we see on the graph, that the higher in temperature we go, the more thermal degradation there will be, and the lower pressure will be along the measurement time. A second thing we studied in with these measurements are the influence of the preheating phase. So as Frederik mentioned before, these variants on the capillary rheometer does this preheating phase in a different way. We have typically the two zones. On top we have the storage zone, which has in our experiments a temperature going from 145 degrees Celsius to 185 degrees Celsius, and the lower, the actual measuring zone, has a temperature of 210, which is higher than the degradation temperature, because PLA typically starts degrading when it's exposed to a temperature above 190 degrees Celsius. So you can see that our storage zone is at a temperature below the 119 degrees, and the measuring zone is below the measuring zone is above the 190 degrees. So that's something important to keep in mind. Because we did two experiments. The first one, there we put our material in the storage zone, and we extend the time that it's here in this zone, and we minimize the time that it's in the measuring zone. And in the second experiment, we minimized the time that it's in the storage zone, and we extended the time that it's in the measuring zone. What do I mean with extending? In the storage zone, extending the time means that when we put new material in the storage zone, normally we immediately press start for the next measurement. When we extended this time up till 600 seconds, we just waited, so it's at a high temperature for a certain time, and then we only start the measurement. And extending the time here in the measuring zone means that we will perform a really low and long measurement at a low shear rate. So these are the results for the first experiments. So on the x-axis, you can see the waiting time. This is the time, as I mentioned, between putting new material in the storage zone and between starting our actual measurements. And we performed multiple measurements, 180 seconds, 240, 300, up to 600 seconds. That is just waiting in the storage room. And then we looked at the pressure, which is measured at a different shear rate. So here we performed a normal measurement, a different shear rate profile. And what we would expect when we expose this material to for more than 10 minutes to these temperatures that are elevated, we would think that there would be a decrease in pressure. But what you can see is it doesn't matter how long we leave it in the storage room, there is no clear trend in a decrease of the pressure that we measure, meaning that extending the time in the storage zone at 145 degrees until 185 degrees does not result into a decrease of viscosity and pressure. And why is that? Because our temperature in the storage zone, which was maximum 185 degrees, is below our degradation temperature of PLA. And that's a good thing because we can keep our material in the storage zone for a long time without having degradation during this preheating phase. And that's really important for bio-based materials. The second part of the experiment was that we we extended this time in the measuring zone, so we keep it there for a long time at 210 degrees, and we can see, as previously mentioned, a decrease in pressure along the time because due to thermal degradation. And that is because our actual measuring temperature was 210 degrees, and it is above the 190 degrees degradation temperature of PLA. So when we compare both of them in terms of the preheating phase, the standard capillary rheometer does has degradation occurring during our storing and preheating phase, because there is only one uniform temperature, which is often above the degradation temperature of our bio-based material. And we will have degradation during this phase where our sample is heated up to its melt phase. And then this variant on the capillary rheometer, there we have to conclude that degradation can be limited during this waiting time, because the temperature in the storage room can be kept below our degradation temperature. And this is really beneficial for our biopolymers because they tend to be really sensitive for thermal degradation. The last effect I want to discuss with you is the effect of moisture. What's important, we always have to dry PLA before measuring it, because PLA and other bio-based materials tend to absorb water from our moisture out of the air, and resulting in an extra type of degradation during measuring. So what did we do? We took two temperatures, 210 degrees and 230 degrees, and we measured one time with dry material, which was dried to the recommended 250 parts per million. And we also did the same measurement, but with not dried material, which was 1,250 parts per million. And we repeated it with a higher temperature. And what can we see here on this graph? Also, again, our long measuring time of 10 minutes, just pushing it through our capillary. And on the y-axis, we have our pressure in megapascal. And we can see for a standard measurement with dry material that we have a decrease. It's 12% almost, and it is large, but it's due to thermal degradation. But when we use not dried materials, this evolves to 55.71% drop in pressure, which is really a lot. So we can conclude here that on top of the thermal degradation, the hydrolysis or the degradation due to water also has a really great effect on our measurement results. And it's important to be aware that our measurement results can be influenced by all these types of degradation. So it's really important to keep a moisture level lower than the 250 parts per million, and it's necessary in that way to minimize our hydrolysis, because it would also lead to a molecular weight decrease and also a drop in viscosity. So just to end this part of the presentation, it's rheologically characterizing our material, and especially thermal sensitive biopolymers. It requires a critical mindset, but you have to be aware of the different types of degradation that are occurring, and you also need a structured method to minimize our degradation. And how can we do this? We have to minimize our residence time, the time of our sample in our measuring machine. We have to minimize moisture level and also keep our moisture level as constant as possible when we want to reproduce our results. And we also want to minimize exposure to high temperatures due to the thermal degradation, because it seems to have a really large effect on our measuring results. So I would give back the word to Frederik. Thank you.
Okay, the final part within this presentation is in fact the upscaling and to see how this is applicable also to be used in real industry, because the results shown by Ineke are just based on lab equipment. So the main challenge is, of course, how do we translate it into real processes. So if you think about industrial processing, let's say the main focus in the PhD of Ineke is to look for extrusion processes. So typically one wants to combine fast heating, and that's the main reason to have a let's say advanced screw inside processing equipment. So the aim is to investigate how much loading can be applied to the material, and so which type of machine is necessary to get the material as fast as possible into a as homogeneous as possible temperature, and before it is transformed into its real shape. So that's the main aim of the PhD. So this upscaling, so to find the link between the material characterization inside the lab towards the real processing on large scale, so maybe several hundreds of kilos per hour. So of course one has to pay attention for moisture content, the mechanical loading which is occurring, which thermal loading is on top of the material, and also which type of machine is necessary. Typically, people or companies bought, let's say, always maybe equipment which is large enough. You never know for the future, and we will buy it maybe one size larger. But in this type of material, that's not of interest, as you maybe end up with too large volumes of material which are already at high temperature. And as previously shown, we have to deal with a lot of decreasing of viscosity, and this hence also means decrease of mechanical performance in the end. So that's the main thing here. So designing the appropriate machine. So we can also use numerical simulation tools to look for the residence time into the equipment. So depends if you have, for example, a extruder which is has a maximum RPM of 150 RPMs. So then you can have a look on these residence times at high temperature. So if you have a too large machine and you run it really low RPM, then you see that you are far off the wanted residence times in the equipment. So in fact, you only want to have it maybe 1 or 2 minutes inside the equipment. So this can be illustrated using the appropriate numerical simulation tools. This is just as kind of example, so that you of course have to use the appropriate machine for your application. So don't buy too large equipment. So based on the results on lab scale and the numerical simulation tools, we are able to predict which residence times are there, and hence or combining the results, we will see which drop-in properties will be there. So in that way, we can state as final goal is in fact to really to define the already state of degradation when you have processed your material. If you have really long and large process, maybe half of your biodegradability has been gone during the processing, which is of course not the aim. The aim of the PhD of Ineke is really to limit this degradation during the processing, to define the optimal processing conditions, and of course also being aware of the moisture level, taking this into account. So what's really happening on top of this to go for a kind of next state in the modeling of this type of materials. So that's the main aim of this research, and already some initial results are shown. So in that way, I want to thank you for your attention, and if you have any questions about this topic, of course, feel free to contact one of us, and I wish you all the best in doing all types of research within polymer processing and material characterization. Thank you.